Hi everyone, my name is Karthik Vaidhyanathan, working as a postdoctoral researcher at the University of L'Aquila, Italy. This work was done in joint collaboration with Mauro Caporuscio from Linnaeus University, Sweden, Marco di Toma, and Professor Henry Muccini from the University of L'Aquila, Italy. Microservice-based architectures have gained great popularity over the last decade due to its large-scale adoption driven by many advantages they offer such as scalability, modularity, maintainability, and the list goes on. The image here shows the structure of microservices at Netflix, Twitter, and Amazon. They all have thousands of microservices that are replicated and deployed at different geographical zones. So this complex architecture also brings in new challenges. As seen in the previous slides, there may be thousands of microservices that are replicated to hundreds of instances and run on different servers. Hence, the main question that arises is how the services discover each other or how an external client can discover a microservice. As depicted in the figure, assume that any client, which can be a microservice or an API gateway, wants to interact with the microservice A, which has been replicated to three instances. As we can see, each of these instances are in different locations. Now, the question here is to which instance of A does a client communicate with? This is accomplished using the process of service discovery. Let us look at service discovery in detail. Service discovery in principle consists of two main steps. One is a match and the second is a select. Match identifies a set of instances that are available and select picks one of the instances for communication. Two main architectural patterns exist for service discovery, client-side pattern and a server-side pattern. In the client-side pattern, as shown in the figure, all the available microservices registers themselves in the service registry component. The client then sends a service discovery request, which in other words is called a service query to the service registry. The registry then retrieves a set of available instance of microservice B and sends it back to A. A then applies a selection criteria to connect to an instance of B. Netflix Eureka is built based on this pattern. One of the major issues, however, with this pattern is the tight coupling between the registry and the client. On the other hand, in a server-side discovery pattern, an additional router component is used which facilitates the discovery. As depicted in the figure, at first, similar to the client-side pattern, all the microservice instances register in the registry. The service A sends the request to the router. The router then fetches the set of available instances of service B. It then performs a selection based on some criteria and then routes to the selected instance of service B. This is one of the most popular service discovery patterns used in technologies like AWS ELB, Zookeeper, and so on. The only disadvantage here is that the router needs to be replicated and managed. It also contributes to one additional network hop. However, since this eliminates coupling, this is more widely used, and in this work, we make use of this pattern. But there are some challenges that exist with existing service discovery mechanism. Most of the service discovery mechanisms perform selection based on quality of service declared by the instances during their registration. However, the quality of service of the instances fluctuate during runtime due to various contextual parameters such as location, time of the day, and so on, as well as due to other parameters like RAM, CPU consumption, etc. Moreover, the context of the client or the service consumer also impacts the selection. This can impact the overall quality of service provided by the service provider. So the main question that arises is how to select an instance that guarantees optimal quality of service based on the context of the service consumer as well as based on that of the provider. To this end, in this work, we propose an approach that uses dynamic context and quality of service data as drivers to perform service discovery. This is achieved using machine learning techniques that are used for learning the quality of service pattern, predicting the expected quality of service, and selecting the instance with optimal quality of service. The figure here shows the overall intuitive idea behind our approach. At first, the service registry receives the service query, which contains the information on the type of service required. Then it extracts the contextual information from the query, such as the location of the client. Following this, it first identifies the microservice and its corresponding instances based on the query. In the next step, the approach uses machine learning techniques to predict the expected quality of service of each of the instance and then further ranks them based on the expected quality of service. Till this step, as we notice, the context parameters are not used. Before the next step, the approach checks if it is the first run of the approach. If it is the first run, then there is no previous learning, so the approach just picks one of the instance and sends it as response. But if it is not the first run, the approach takes the feedback of the previous selection by looking up what was the actual quality of service when a selection was made in a previous run for a given context. It then learns from that experience and then selects an instance and returns it as a response. This two-way learning allows the approach to improve with every selection performed. Let us now look at the approach in detail. The figure here shows the high-level architecture of the machine learning-driven service discovery approach that we have developed. With each microservice instance, there is a monitoring component that is responsible for monitoring the different quality of service and context data such as time of receiving a request, response time provided, throughput, CPU, etc. Below we can see a set of components which are responsible for data collection, building machine learning models. The monitoring manager component is responsible for collecting all the monitored data from the instances and for ingesting them to a repository. This data is then used by the model builder component to perform training and build machine learning models for quality of service prediction. The model builder makes use of deep neural networks for building the models. These models are then sent to the quality of service predictor component. So during the process of service discovery, as we know, the service consumer, which is service A, first sends a request to service registry asking for the instances of B. Following this, the quality of service predictor component is responsible for using machine learning to make predictions of the expected quality of service of each of the instances of B. The selector component then uses this information along with the context information to make selection using reinforcement learning. It then forwards the request to the selected instance and provides a response. What we see here is the overall flow of the approach. It is divided into two phases, the batch phase as well as the real-time phase. The batch phase represents the set of process involved in building machine learning models. Since it is a time-consuming process, this phase is executed periodically. As we have seen in the previous slide, the quality of service and the context of all the instances are stored in the repository. These data represents raw quality of service and context data of every microservice instance. The important thing to understand is that these data have a temporal nature and we can exploit time series forecasting techniques to predict the expected quality of service. To this end, the data is extracted from the repository through a data extraction process, and this is further sent to the feature extraction process. Feature extraction process creates a uniform time series data using the data available, and then this is split into a training data as well as a testing data. The training data is used by the training process, which makes use of recurrent neural network, in particular long short-term memory network, to create forecasting models. This model is then tested using the testing data and further used by the prediction process. Now, during the real-time phase, the service registry receives a service query based on which it identifies a set of instances that satisfies the query. For each of the instance in the instance set, the prediction process forecasts the expected quality of service and then creates a rank list based on the quality of service. This is then used by a selection process which makes use of reinforcement learning, in particular Q-learning, to select the optimal instance, also considering the context. This is then sent as the response. The figure here shows an intuitive view of how the selection algorithm works. As mentioned in the previous slide, it uses Q-learning, which is a model-free learning technique. This means that it does not require any pre-trained model, rather the learning happens on the fly. At each step, first the selection process receives the context of the consumer. It then observes the different instance choices it has. Based on the predicted quality of service and context, it then classifies the instance into different discrete states as denoted in the figure. So for instance, instance 1 is in a state of high response time and context C1. Instance 2, on the other hand, is in low response time and in context C2, and so on. Now, it uses a policy to select one of the instance here. Let us assume that it selects instance 1. We know that this was a wrong choice because it was going to incur a higher response time. This means that the selection process will receive a negative reward or penalty for the selection. It then updates this learning so that in the next step, it remembers the feedback and performs a better selection. This process continues, enabling the process to improve with every selection. Let us now check how we evaluated the approach. To perform evaluations, we used a proof of concept microservice-based coin collection application. It consists of 5 major microservices for handling different functionalities such as user authentication, storing coin details, retrieving coin information, storing user details, and so on. For experiments, each of the microservices were replicated to 5 instances, making it a system of 25 microservices. For service discovery, we created a custom Java module which provides interface that supports integration with existing technologies like Apache Zookeeper, Amazon ELB, and so on. We used Keras for building the machine learning models and native Python for building the Q-learning algorithm for selection. The application was deployed in Google Cloud using two virtual machines. Each virtual machines were running in different geographical zone. One was set up in Europe and one was in Europe and one was in US. Each had different number of cores, RAM, processor, and so on. All this was done to capture the different contextual parameters. For building the initial machine learning model, the application was deployed without using machine learning for a period of 1 week and the data was collected. The workload simulation was performed with arrival rate based on a Poisson distribution. We use response time as the quality of service that we want to optimize and location as well as the time of invocation as the contextual parameters. These were then used to build LSTM models with a forecast horizon of 5 minutes. As regard to the evaluation candidates, we used 5 candidates as depicted in the table. The first candidate formed the naive baseline that does not use any machine learning but uses a greedy approach for selection based on the declared response time. The second one uses simple linear regression for forecasting the response time and then greedy approach for selection based on forecast and so on. The final one represents our approach. Now, concerning the evaluation metrics, we used root mean squared error for evaluating the forecast accuracy. For measuring the effectiveness of the selection process, we used two metrics. The first one captures the average response time delivered by every instance for a given time t, and the second one captures the response time perceived by the service consumer. So the figure here shows the plot of the actual response time versus the forecast produced by the LSTM models on the initial testing set. As we can see, the forecast is able to follow the actual values with an error of 406 milliseconds. This is just based on the initial testing set. In practice, the model keeps improving with the execution of every build phase. For evaluating the effectiveness of the overall selection, the approach was run for a period of 3 days using each of the evaluation candidates. The first plot shows the cumulative response time offered by the instances at every instance of time t. We can clearly see that time series Q-learning is able to provide lower response time. This is due to the ability of Q-learning to continuously improve the selection process based on feedbacks. The second graph shows the average response time perceived by the client. Here also we see that our approach is able to provide a lesser average response time compared to other approaches. In fact, about 20% better than the naive baseline. We can also see that there are higher outliers in our approach. This is due to the initial phase of Q-learning, which leads to incorrect selections. Concerning the efficiency, our approach on average took around 0.10 seconds to perform the overall process, including prediction and selection. In this, the major time was consumed by the prediction process, as the prediction has to be made for each of the service instance. Okay, so the major contribution of this work is an architecture for learning-driven context-aware service discovery. We believe that this will serve as a reference architecture for architects for future integration of machine learning with service discovery process. The second important contribution is that our approach supports ways to easily integrate machine learning with existing architectural stack as opposed to traditional deployments, thanks to the build and real-time phases. We were also able to see that the effective use of machine learning techniques guarantees higher quality of service while performing service discovery, and this in turn was able to handle the uncertainties related to the transient nature of quality of service of microservices. Finally, we were also able to shift focus from a traditional reactive service discovery mechanism to a proactive mechanism with the help of deep learning and reinforcement learning. So concluding, in this work, we have presented a novel approach to service discovery in microservice-based architectures. We saw how our approach effectively leverages machine learning techniques on the context and quality of service data to improve the overall quality of service. Future work include, but not limited to, extending the approach to large-scale systems with larger instances that considers multiple quality of service parameters using trade-off based mechanisms. We also plan to explore the possibility of using transfer learning to see if we could transfer the knowledge gained by a Q-learning agent in one system to accelerate the learning process in another system. So thank you, and we'll be happy to answer your questions.